Welcome back again to Educator.com. We'll have another lesson in intermediate C++. Today we are talking about containers. It's specifically list containers, linked lists. All right. Now we're going to talk about a few things, including a brief comparison of a linked list and vectors. We had vectors last time. We have linked lists this time. So we're going to overview how linked lists work. We're going to compare them a little bit to how vectors work. We access the list elements via a method and via iterator. We've talked about iterators before. We're going to compare the vector iterators to list iterators. They're subtly different. Get the information about a list, modify the list elements or the list itself. We'll modify the list. We'll have some examples. We'll merge, splice, sort, and reverse a list. A list is, like a vector, is a sequence container. So the sequence is important. And we'll provide some functions for custom sorting. You may not like the way the system sorts things. The system may not be able to sort your object without you giving it a custom sort routine. And a few other containers that use the linked list, container adapters, specifically the deck. It looks like DQ, but it's pronounced deck, stack, and queue. All right, a little quick overview here. Now, we've seen arrays and we've seen vectors. The data is kept in contiguous memory. Now, here's a nice little picture. We've got some numbers. I'm not going to read these numbers off for you. Insertion and deletion can be expensive. You see, we have a 271 we want to put in there. We want to put it in this particular location because we want to keep it in order. Now, what that means is we got to move that to there, that to there, that to there, blah, 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 until we get to the end. Now, if this is going on for hundreds or thousands of elements, you can see this may take a little bit of time. Erasure, removing deletion is the same problem. So we want to erase this one. Well, guess what? We have to move all the other ones over all the way. And now if there's hundreds and thousands of them, that can take a little while. It can take a long time, not only in computers. You say, well, computers are fast, they take microseconds. Well, no, sometimes it can take a visibly length of time. You're sitting there waiting for it to do something. A human perspective, long time, depending on what you're looking at. I mean, these looking at all these are integers. What's the big deal? Those could represent, instead of integers, they could be a large, complicated object that you've designed, and you have an array of those objects. And if you have to physically move all of these objects, it could be time-consuming. So if you need to do with a lot of insertion and deletions, an array or a vector may not be the container you want. Now, your linked list container solves that problem because the data is stored in these nodes, and the nodes are scattered all throughout memory. So here we have the 15 is there, the 27 is there, the 82, blah, 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 all the way around here. So now when we have a new node we want to add, we don't have to move anything around. All we have to do is take this pointer that's from the 267 to 275, and erase that pointer and have it point along this green line to the 271, and then have the 271 point to its next, which is 275. So now we've only moved a couple of pointers around, and now all of a sudden the linked list has got a new node in order where you want it. Here's a brief description of how something like this might look as a structure. We have a struct linked node. Double is the value, which would be like 342 or 271 in this case, etc. And then a pointer to the next node in the linked list. Here's how we define the top pointer, which points to the top of the linked list. From the top, you can go to the next, to the next, to the next. Sometimes it would be called the front. In this particular case, I happen to call it top. And I have a temp pointer, which you can use to I need to save the previous pointer while I'm moving things along using a temp. We also have new node, which I did not define down here. It should have, which happens to be pointing to the node you want to insert. But accessing the nth node. There's trade-offs everywhere you go. If you need to access the nth node, it may not be as cheap as an array. With an array, you've got your pointer to the first spot of the array. I need the 27th node. Well, you take this point, you add 27 to it, and I don't know where we are, and let's say it puts it at this position. So this address plus 27 points you right to where you want to go. Linked list, you start here, you start counting. Go to the next one, go to the next one. And each time you go to the next one, you increment your pointer till you get to number 27. Here's our 27th node. So you have your trade-off between being able to insert and delete quickly and being able to access a specific node quickly.